about that. Hey everyone, this is Michael from the Data Incubator. We're really excited to have you for another installment of Data Science in 30 Minutes. So maybe before I begin, we'll wait a minute or two to let folks sort of slowly trickle into the room. I know that there'll be a lot of folks who are sort of joining us from all over the world. We had over 2,000 signups for this, and we're really excited about that. All right, so I'll take a few minutes maybe to introduce myself, the Data Incubator, and what we do before I turn it over to our speaker, Matei Zaharia, who's been nice enough to join us from a sunny location in Palo Alto. So I'm Michael Lee, the founder of the Data Incubator. So we're a data science training and education company. So we help we are probably best known for a fellowship we run that helps PhDs and master's students who are looking to transition out of academia and enter industry as a data scientist. And the program is completely free for the fellows who get in. And if you're interested, you can apply online at thedataincubator.com. So that's just www.thedataincubator.com. We also do corporate training. So for a lot of companies that are looking to get their staff trained up on data science and AI, you can also sign up for that. And of course, hiring data scientists who are coming out of our data science program. So you can also sign up at www.thedataincubator.com. So today we're here to talk about data science in 30 minutes. This is a regular monthly series that we do on data and its role in the world. Just to give you a sense, some of our past speakers have included Becky Tucker, who's a data scientist at Netflix, Jess Strauss, the VP of data at Quantopian, Holden Corral, an engineer at IBM and one of the core contributors to Apache Spark, Andreas Mueller, who is one of the creators and core maintainers of scikit-learn, Sam Swift, VP of Data Science at Betterment, who's also, by the way, a former fellow at the Data Incubator, as well as many, many others. So before I introduce today's speaker, I want to remind everyone that you can pose questions in the YouTube chat area. So this is just the YouTube page that you're on. There's a chat area on the right. And we'll be monitoring those and we'll pose them at the end of this to anyone who has any questions. Now, you do need to be logged into your Google account in order to pose questions to the speaker. I'm not even sure if you can view this without being logged into your Google account, since I'm perpetually logged into one or some other Google account. But if you want to ask questions, please do just log in. So without further ado, I'd like to introduce Matei Zaharia. Matei is an assistant professor of computer science at Stanford and also the chief technologist and the co-founder of Databricks. His research interests broadly span data-intensive systems, including distributed computing and systems for machine learning. In his past research, Matei has developed a widely used open source software, probably best known for Apache Spark and Apache Mesos, which is a cluster management software. And his research was recognized in the 2014 ACM Doctoral Dissertation Award, as well as the VM Systems Research Award. So without further ado, I'd like to turn this over to Matei, who will be speaking to us about usable machine learning.
All right. Thanks a lot, Michael. Hopefully you can hear me, right?
Yeah. Loud and clear.
Okay. Thanks. Yeah. So yeah, excited to be here today. Thanks to everyone who showed up. I'm going to actually share my screen now. I'm as Michael said, I'm part of both the research and the kind of commercial and open source communities. So I'm a chief technologist at Databricks. I continue to do a lot of things with Apache Spark, but I also have a research group at Stanford. And in this webinar, I'm going to talk mostly about research that I'm doing with 3 other faculty colleagues at Stanford as part of the DAWN project, which focuses on infrastructure for usable machine learning. So this is kind of more cutting edge stuff. Most of this is actually open source. These are projects you can try out today, but they're like a little bit earlier on, a little bit kind of farther out there, but they're kind of the direction that we think the field is going to go for usable machine learning. And there's a lot of exciting stuff in this space. So this is, again, work by 4 different faculty members at Stanford: Peter Bayless, Kunle Olukatun, Chris Ray, and myself. Some of the projects are just by some of the people, some of them are joint projects, but we all kind of sit close together and have this common research group called DAWN. Oops. Okay. So just to jump right into it. 1 second. Let me figure out how to do this. So everyone kind of knows or acknowledges that it's kind of the golden age of data right now. There's incredible advances in all fields related to data and machine learning, things like image recognition, natural language processing, planning, information retrieval. In many of these, you can get algorithms that are starting to approach sort of human capabilities for some of these tasks. And these things are starting to have society scale impact with things like autonomous vehicles that are actually driving around, personalized medicine, real-time translation, and so on. And there's no end in sight for these advances in machine learning. But if you look at it a little bit more closely, there's a little asterisk or caveat with this. So it is the golden age of data, but only for the best funded and best trained engineering teams. Every machine learning product that that's really moved the field forward or that's been successful has usually required a team of hundreds to thousands of engineers, as well as other people working together to build that product. So if you look at things like AlphaGo or Siri, or even beating the the ImageNet data set, is very large efforts that are required to do these. And the interesting thing with this is, if you look especially at commercial projects, most of what those people are doing is not actually sitting around and modeling things for machine learning. Most of it is actually things around the machine learning, such as data preparation, model tuning, experimentation, and productionizing the system. So being able to feed it continuously with new data, monitor the quality, react to problems in it, and so on. So in each of these projects, there is, of course, a small team of people who are sitting around like coming up with new machine learning models or doing math, but then there's hundreds, maybe thousands of engineers involved in the infrastructure. And the effect of this is that if you're just a domain expert in some area, like say you're an expert on medicine or on fraud or something like that, it's not easy to build machine learning products because you need all this supporting infrastructure. So we're not the first group to say that. Actually, even in organizations that have a lot of software engineers like Google, they realize this problem. So this is a white paper from Google called Hidden Technical Debt in Machine Learning Systems, where they talk about experience building a bunch of production systems. And this is the diagram they have in the middle. And you can see in this, there are all these boxes for what you need. And there's a tiny box in the middle for machine learning code. And then everything else, way more code and way more effort, is around things like data collection, data verification, serving infrastructure, monitoring, and so on. And those are the pieces you need to actually have a working system. It's not enough to have that little demo where it predicts something correctly on one data set. So our question in DAWN is what if anyone with domain expertise could build their own production quality machine learning products? How would that look like? What would the infrastructure look like to build that? So we want people to be able to build these without a PhD in machine learning, without being an expert in computer systems, without understanding the latest hardware. But of course, they should have knowledge about some domain. Like, for example, if you're a finance person, maybe you just know about fraud and you want to build a machine learning system for that. And it seems, I just said that you need teams of hundreds of people to do this. So like, why, how can we possibly do it with fewer? But the thing that we observed is that this has actually happened before in other areas of computing. We've had many areas where, things used to require an enormous team of people. And after defining the right infrastructure and the right workflow, those technologies were basically democratized where anyone can use them. One of my favorite examples of this is actually search. If you look at search, it's a field that's pretty similar in many ways to machine learning. There are many different algorithms, data structures, and metrics involved. There are still really active research conferences you can go to about information retrieval and ranking and so on. And it's also a field with, where the results are somewhat soft or probabilistic in some sense. So like you need some human judgment to figure out whether they're good. But if you look at the way search software has evolved, we've managed to package that complexity into an interface that many developers can use without having to attend all the search conferences and read all the literature in the past. So any developer today can add search into an application by just linking in a library such as Solr or Lucene. And any computer user, even non-experts, know how to use search, and they kind of know, how these systems work, when they might break down, and stuff like that. And so you have this really powerful abstraction built on, basically decades of research that anyone can use. And it's super easy now if you build a web application or a mobile application or anything like that to add pretty reasonable search to it and maybe to tune it and make it work. So the key idea in here is that, beyond developing this technology for how to do search, people developed end-to-end systems such as Solr or Lucene that actually package it inside, a suitable interface for others to use without having to be an expert on all the internal details. And these systems tackle the whole life cycle, not just, say, building an index once, but everything you need for production use, which is where all of that effort is. So the scalable serving, the live updates of the index, all that stuff is handled automatically in a single system. So this is the type of work that we want to do for machine learning. Of course, machine learning is in some ways more complicated, but we want to identify the abstractions and the systems that will allow sort of thousands of people in an organization to reliably use machine learning instead of requiring, a single team and many sort of months of effort for every project. And so to do that, we're building this stack of software systems in our research group that span the whole range of machine learning, all the way from data acquisition to productionizing the models, and also that span different layers of the software stack. So all the way from new interfaces that humans can use to build and model and debug machine learning applications, and all the way down to systems and hardware that these things execute on. And to give you just a sense, I'm going to show you a few of these. All of the ones that I'm showing are open source projects as well that you can use. Many of them interact really nicely with the existing open source ecosystem, such as Apache Spark. And they are research projects, but I encourage you, if you're interested, to reach out, talk to the PhD students involved in it, and try it out, because people are excited to see others use these. So just to start with, I'm going to show one of the systems that actually kind of achieves this end-to-end vision for one task, which is MacroBase. It's a system for analyzing streaming data, and it's primarily developed by Peter Bayless, one of the other PIs here. So MacroBase has a really simple kind of interface and abstraction. So basically, it's a system for continuous analytics that's whose goal is to help you identify anomalies or groups in the data that have anomalous properties compared to the rest of your data. So the input into it is multidimensional data streams. For example, say readings from a bunch of sensors, or measurements from a mobile application, or even logs in a data center. And the output is MacroBase identifies and ranks the groups that have anomalous behavior. For example, all the cell phones running this version of the operating system have way lower battery life, or something like that. And it can identify groups including multiple attributes, and it actually solves a somewhat difficult algorithmic problem in there to do that efficiently and in real time. So just as an example, I'll show some data from a mobile application. That's actually one of the early use cases of MacroBase, is this real kind of mobile application. And you can see this is kind of what the data looks like. It's basically a table with readings from different phones. And there's lots of information about each phone. There's like the user ID, their location, which state they're in, the hardware make, hardware model, app version, all that stuff. And there are also some metrics such as battery drain and average temperature. So if you just look at this data, it's really difficult to spot any kind of patterns or anomalies in it. Like, you might see, oh, the battery drain is high in some case, but is it consistently high for a given state or for a given hardware, or maybe a combination of like this hardware model and that app version? It's really hard to tell. And it's even harder to do this when the data is streaming. It's very difficult to actually make sense of it. So in MacroBase, you get an API or also a small user interface where you can find these anomalous groups automatically in a scalable way. And basically what you do, you connect to your data and you select some metrics of interest, such as, for example, power drain. And you also select which metrics you want to consider as attributes that are correlated with it. And MacroBase will efficiently search the space of all of these and give you a list of outputs that are sorted by how anomalous they are. That looks a little bit like this. So this is one of the outputs. It says it found this group of records that are significantly different from the distribution. So records where you have app version 50 on this particular hardware model of the phone have about 400 times basically higher battery drain than other records. So this is an anomalous group. And MacroBase will automatically sort these groups. It can also give them to you in a streaming fashion, and it can actually scale out over large clusters as well using Apache Spark. So the cool thing about this is it's an end-to-end system to do this really common task of anomaly detection, where you don't need to know about what it's using internally to do this. Internally, it's using a bunch of sketches, it's using a bunch of frequent pattern mining algorithms, and it also has a bunch of optimizations that modify these for this specific use case. But you don't need to sit down and code up all of those. As a user, you can plug it in, and you can reliably find anomalous groups according to something you understand, which is basically this ratio of how anomalous they are. And so you don't need ML or algorithmic expertise. You don't need a separate step for production use. The same system supports production, and it's been co-designed internally so that all these things work. And the really cool thing about this system is we've run workshops on it. We've let and it is open source, and we've let people connect to it. And nearly everyone, when they plug in a data set, they immediately find some interesting anomalous groups. And so it's been used by automotive companies, cloud media companies, mobile applications, and more. And several of these are actually now running it in production to monitor, large internet services that people are using, and to find outages or anomalous behavior. So it's a pretty cool way of packaging and defining software for this particular use case. And it shows kind of this idea of how can we democratize ML. You can find out more about it on the website. I'll talk about a couple of other projects as well to go across the whole stack and to show you. So these will be more focused, but I think they're also interesting because, again, they focus on what's the pain point for end-to-end use of ML, which is often very different from even what a lot of the machine learning libraries focus on, which is just training a model. That's like the small black box in that figure. So next thing I'll talk about is for data acquisition and feature engineering. This is Snorkel, which is a project by Chris Ray, one of the ML faculty in our group. So the key observation in Snorkel, the key problem it's tackling is acquiring training data. And if you're familiar at all with machine learning, you realize that training data is really the key to AI. If you have lots of high quality data, AI is actually easy from a statistical perspective. On the other hand, if you don't have high quality training data, it's no amount of artificial or human intelligence is going to help. So just as a picture to show that, here's an example of trying to predict how much of a loan people will repay, say, based on their credit score. Imagine we're a company that's trying to do this, but we have very little data. And someone comes in with a credit score that's in the middle here between what we've saw. Well, regardless of what amount of AI or whatever we use, we can't really infer too much about this particular point because we just don't have a lot of data. We know there seems to be a trend where the amount we paid is going up. And we could guess like, hey, maybe with this credit score, there's somewhere in here. But there's not much else we can do. Is no amount of modeling is going to help in this scenario because we just haven't logged a lot of stuff. Now compare this with a company that actually has acquired more training data. In that case, predicting the amount we paid for this credit score is super easy. There are so many other data points that are really close to it. You can safely guess not only kind of an expected value, but probably some kind of confidence interval. And again, from a statistical or AI perspective, this problem is actually easy. So you'll notice that to actually do statistical modeling, we need these data points, and in particular, we need both features and labels. Just having lots of credit scores without knowing how much they repaid wouldn't be enough. So these are the things. Now, if you look at where AI has been successful today, it's extremely successful in fields where getting labels is easy. So things like image search, speech, playing games like Go, where you can just look at lots of human games or play against yourself. Label training data is both cheap and easy to obtain there. You can just find lots of text online, lots of recordings of people speaking and stuff like that. And that's where the major successes with AI have been. It's no accident that's where they are. On the other hand, if you look at many of the places where people want to apply this, beyond the web, things like medicine or understanding documents, like say legal documents or tech support comments or things like that, or fraud detection, getting labels is much more expensive because you need a human expert to actually get those labels. You're not going to find on the web a lot of like labeled X-rays that tell you where the cancer tumor is or something like that. You're not just going to find that on a bunch of websites. So the key question in Snorkel is, hey, when your labeling is many times more expensive, how can we leverage data that's expensive for humans to label at scale? And obviously, the more we could label it, the better we'd be able to do. So Snorkel's approach is a new interface for the human experts to interact with the machine learning system, which is weak supervision. So in traditional, machine learning, you just have labels. So your interface to the human is just, hey, here are a bunch of images. Please give me a label for each one. It's very time-consuming for the person, and their input to you is just like a 0 or 1 for each image. This has a tumor in it. This one doesn't. In Snorkel, the interface is actually different. You tell the user, give me a function, give me a program that I can apply to unlabeled data that will guess what the label is. So for example, maybe the user doesn't have time to read lots of documents and to tell you something about it, but they can give you something like a regular expression. Like if this is a claims form that mentions, the following word, it means it's probably about, this type of product, or it means it's probably about this type of problem with the product. And so basically, you get these labeling functions. They're cheap to apply at scale, but they're potentially noisy because they're just a function that the human gave you. And then what Snorkel does is it solves an optimization problem where it simultaneously learns the noise in these functions, as well as a noise-corrected target model for the machine learning problem you have. So for example, you can train an LSTM on your text data using these noisy functions, and Snorkel will basically correct for them and give you the best model that fits them and that kind of matches these functions, knowing that they have noise. So it's a very powerful technique, actually. It turns out that when you talk to human experts who do lots of data labeling, they actually frequently have these types of rules. That's what they're doing in their head. And if you tell them to give you the rule, instead of just asking for like a 0 or 1 on every item, they actually give you a ton of information that leads to good models. So just as an example of this, Chris's group worked with several groups at the medical school at Stanford. And these groups are trying to automatically read papers and patient reports and identify things like interactions between drugs and so on. So that's what they're doing. So in these groups, there used to be, there were these graduate students that would spend like a year or 2 years reading lots of scientific papers and labeling them to say, oh, this is what the paper is about, and it shows that this drug interacts with that one, in order to feed that into a machine learning model. That's just what they did. Chris's group got these students to just sit down and spend 4 hours listing a bunch of labeling functions, so like some of the rules they use, and basically coding them up in Python. And it turns out that if you take 4 hours to write up these functions and then you apply them to a large data sets of millions of previously unlabeled documents, you actually get the same results as what these students were doing before, where they hand labeled a few tens of thousands of documents. And of course, you did it in much less time. So you get these high-quality models from these low-quality but scalable functions that you can apply on all your data. These are just some results of the different F1 scores they got on different data sets. The point here is just that using Snorkel, they match, or in some cases exceed, the state-of-the-art F1 score with significantly less work. And Snorkel can be used with an arbitrary downstream model, including logistic regression and LSTM and others. So again, this is an open source system. It's actually in use by sort of dozens of companies and groups already, and it's based in Python. It's really easy to run with tools like scikit-learn as well as Apache Spark. So I invite you to check that out. And it's this new interface that's making it much easier for people to use machine learning. And then the final system I'll talk about is on the inference side. This is a system that I am working on along with Peter Bayless, which is called NoScope. And this is for fast inference, which is also often a problem when you're using machine learning, especially deep learning. So the idea in here is, okay, you've trained the model, it's really good, but now you want to apply it to a large data set. It turns out that actually for some of the best machine learning models, the ones that are getting the human class accuracy, inference is extremely expensive. So in this case, we looked at one of the most expensive domains, which is image processing on video. So convolutional neural networks, CNNs, allow you to do really accurate queries on visual data. And everyone has visual data in many different domains. They would love to be able to query it using machine learning. But the problem is that the deeper the models are and the more sophisticated they are, the slower they get to run. So for example, the computer vision community publishes what they call real-time object detection models, some of which are actually optimized for speed, not for accuracy. And even there, the fastest of those can run at about 30 frames per second on a modern GPU. So if you think about it, just processing one video stream in real time, which you get from like a $1 camera you can install wherever you want, to cost you a $1,000 GPU. So this is not going to scale for many use cases, including just monitoring, like a small factory or something like that. I'm not even talking about like a city scale or like sort of scientific data type of video collection. So what we're trying to do is give you the same accuracy as these CNN models, but significantly faster. And so we built a system called NoScope that uses several techniques to do that, to give you 2 to 3 orders of magnitude faster video inference with a small, close to 1% loss in accuracy. So there's a couple of key ideas in NoScope. The first one, which is really interesting, kind of general idea that we're studying in other places too, is model specialization. So when you look at these CNNs, these models are very large, but it's partly because they're supposed to be able to identify thousands of object classes in thousands of conditions, real-world conditions. Like, for example, is this a dog? Is this a panda bear? Is this like a plant? And then is it upside down? Is it in a specific lighting condition, and so on? So what we do in model specialization is we take one of these large target models and we use it as a teacher for a smaller specialized model that we train for each video stream. And the idea is that specific video streams require less knowledge to identify most of the frames. For example, if you look at these bus images here that are from a webcam in Taipei, actually, they all see buses from one angle. They don't need to deal with a bus that's upside down. So what we do is, using this model, we train a much smaller specialized model, and the small model also outputs a confidence score. So when it's unsure, we can still call the original. But on many frames, the small model is sufficiently confident that we can safely use its prediction. And so we can save, basically 99% or more of the cost by calling the small model. And then the second thing in NoScope is, you can imagine in designing these models, there's trade-offs between accuracy and performance. So NoScope also includes an optimizer that automatically tunes a model cascade. So basically figures out the best sequence of specialized models you can use for a query, and it can adapt it in real time as well to the video. And using these two techniques, you can get very large speedups at kind of minimal or to no loss to accuracy. So this is, we have a research paper about this, and we have open source code. This is just showing sort of the easiest and hardest videos from that paper. And you can see in both cases, we can get about 40 times faster at 99.9% accuracy. And if you're doing a query like counting instead, where you're OK with less accuracy, we can go hundreds to thousands of times faster. So it's a really powerful technique. As I said, we're working to apply this in other areas as well, not just video. But it's much like weak supervision. This is the kind of a tool that might become an important kind of thing you have to think about to actually build products. And definitely a lot of the commercial ML products you see, like Siri and Alexa and so on, have, at least for some problems, they do focus a lot on optimizing inference, and they may have some techniques similar to this as well. So that's kind of a brief overview of some of the example projects. There's obviously a lot more in the stack. There's actually quite a bit of interesting hardware and systems work that I'm involved in as well, on automatically compiling these workflows to modern hardware. There's a lot of work on specific types of data and specific types of algorithms, and some interesting ideas around debugging and like new interfaces for that as well. So I'd love to be able to talk about more of them in detail. But basically, if I were to summarize, the main takeaway we have in this project, and the main focus, is that machine learning systems can do more to support user applications end-to-end. And in many real-world settings, if you talk to any data scientist doing something, they'll tell you that the data prep and the productionization and model management and stuff are 80–90% of the work. So we're trying to figure out what are the abstractions and systems for that will enable more people to do machine learning. And then the final thing I'll mention is just a couple of events and things that we're running to keep in touch. So one thing is on the Stanford side, our group organized this conference called SysML on Systems for Machine Learning. You can use to find other academic work in this area. We're also organizing actually a benchmark for deep learning systems that's got some pretty interesting entries, including comparing TPUs to GPUs and things like that. And then the other thing I'll mention that I'm involved in on the Databricks and Spark side is Spark AI Summit in San Francisco. So we've decided to expand basically the Spark Summit conference to also talk specifically about productionizing AI. And a lot of the challenges I talked about here with data preparation, monitoring, model management, and so on are featured heavily at this conference. So I think we'll have an awesome program there for these kind of AI in production type of questions. And I have a special discount code here that you can use to sign up if you'd like to attend the conference. So thanks a lot, and I'm happy to take questions.
Wonderful. Thank you so much for that, Matei. Can you hear me, Matei?
Yep, I can, yeah.
Cool. So, as we said, I think as you said earlier, most of the work in doing data science is still in data munging. And it seems like you have tools that help make that easier, but it also sounds like your tools very much rely on the domain expertise of experts, right? Do you sort of see a world in which that can kind of go away, or do you think that sort of that human expertise is still
useful? That's a great question. I think the domain expertise for the specific problem will be required at least for a very long time, because partly because you want, in the extreme case, like, you're still going to need a domain expert to just validate the model and make sure it's okay, right? Or like validate the results. So for example, like, let's imagine like a medical thing or a like a fraud detection thing. Even if you gave them a list of like, oh, I think these things are fraudulent, someone needs to look at it in order to decide whether to use that in production and like actually go and sue that person or like whatever it takes. So our hope is basically to empower the domain experts, so kind of reduce the effort they need to do, and also to empower the machine learning engineers and data scientists as much as possible, so that they can focus on like, what's productive, what requires a lot of knowledge from them, and they can interact with the domain expert in a good way to build these models. So some of the stuff like, understanding what the data means and preparing it and like figuring out which data sets to use, you'll need help for. But these things where like, the data scientist goes to the domain expert and says, oh, I can solve this problem, just label like 1 million documents for me, maybe can go away. And then both people are more productive.
Absolutely. And do you see, at least in the foreseeable future, do you see a world in which people who are complete novices to both machine learning and coding can do this? Or do you think it's still sort of some expertise in the domain?
I think in some areas you won't need to know about coding or machine learning to do this. And one great example of that is the MacroBase work I showed. So internally, it's basically using, like, depending how you view it, you could say it's doing a kind of like lasso regression or feature selection. There's different ways you can set it up. It's basically trying to select which features among the combinations of groups correlate with some output. But you don't need to know, you certainly don't need to know what that is, or even exactly how it builds it, in order to understand what it gives you. So like, your interface as a user is, you say, I want groups which have at least this many records, and where the ratio of the metric is like at least this much over the rest of the population. So for example, we've had, say, DevOps people who monitor a bunch of servers and monitor like a video delivery application online. They're using this to figure out, when a video doesn't deliver, is it because one of my servers is broken, or is it because my client doesn't work on iPhones anymore, or is it because like, this version of Windows doesn't do networking properly or whatever, and they don't need to know any machine learning. It's the search example I gave is another one where everyone knows how to use search and like what it means when it gives no results and when it gives some results, and they don't need to really understand the internals to use it productively.
Yeah, that's a really good point. And just to sort of riff on the MacroBase example, so in that one, I think you found the case in which I forget what feature it was, but the end result was sort of 400 failure rates that are 400 times more likely than the base case. But in general, do you see that as a use case where it's sort of like probably very, very clear, and you don't really need statistics to tell you that? Or do you sort of see a role for hypothesis testing?
No. So actually, this is in a lot of these cases, it wasn't very clear. So there's a few different ways that this can happen. One way it can happen is, imagine like again, your typical like operator of a large like web service or a mobile app. They look at the overall graph for their metric, and they say, oh, overall, like, everything is 99.9% successful. So that sounds awesome. But maybe within that, there's a small population. It's not a lot of people, but they're getting really terrible experience. So they're not going to notice this unless the experience is so bad that someone from that population complains. Whereas this approach here of running MacroBase, actually, in some of the companies using it, they just run it on the same dashboard as their production monitoring. It automatically gives you a list of the top anomalous groups, and then you can look at those all the time and say like, oh, I didn't expect that to be in there, or like, yeah, actually I did expect it to be in there. Especially the groups that are defined by multiple features, they're really hard to find. Even if you plot by one specific feature, it's going to be hard to notice them. So a lot of it is for proactive stuff. When you have a really bad problem, people will do debugging. And what we found is many people collect data, and then they never look at it unless a problem happens. And then they like trawl through it and find these issues. But for the proactive monitoring stuff, this has helped people catch unknown issues in advance and like actually improve service significantly for some populations of users. Yeah.
And one of the online questions was, do you have to worry about multiple comparison testing?
Yeah, so that's a great question. Yeah, so MacroBase does take that into account, and it uses basically a correction for multiple hypothesis testing. One of the cool things with the setting in MacroBase is you have so much input data that, I mean, you can actually test a lot of hypotheses, especially for this type of monitoring data. And I should also mention, actually, MacroBase is also one of the tools that we're using for just data munging in general. It's good for that. Like, for example, if you want to figure out, like, is my training data from today different from yesterday? It's a pretty cool tool. It just gives you a summary. It says, yes, today you have way more of like these types of items. Maybe you wanted that or maybe not. It's also interesting for monitoring the result of the ML model itself. Like, hey, my model is consistently saying no on like people who live in this area or whatever. So it's the core thing is basically summarizing large data sets or computing differences of large data sets, basically.
So I guess it works really well in this sort of case where you have very tall data, like lots of instances.
Yes, lots of instances,
compared to how wide the data is, number of
features, exactly. Right? It's not going to help if you have this small, like only 100 examples of something. There's not much you can do about that. Yeah.
Okay.
Yeah.
Cool. And then while we're on this theme of kind of feature engineering, where do you, so I think somebody asked a question, and maybe I'll preface it by saying, the dream around deep learning and neural nets is that that takes care of the feature engineering for you.
Yeah.
Right. Where do you see we are with that? Where do you see we'll be going with that? How important is feature engineering going forward?
Yeah, so that's a good question. I mean, deep learning definitely has helped tremendously in that space, but you still really need to understand the type of data that's going in, and to some extent the feature is being chosen. So it will kind of depend on your setting. So for example, for images, it's very common. Actually, most of the results you see where someone used deep learning for, say, medicine or something, they're using transfer learning, where you learned something about images in general, a featureizer for images in general on the web, and then you apply it to something. But there are also cases where, especially if you do fine-tuning, but maybe even if you don't, where deep learning might focus on features in your data that are not really the ones you want. So a good example of this is, like, let's say you're looking at images of, like, say, X-rays from different hospitals, and then one of the hospitals is treating cancer patients, one of them isn't, and then you want to learn about cancer. Well, the problem with just taking your off-the-shelf featureizer is when you apply it to those images, it might learn a feature such as, like, like X-rays from this X-ray machine are blurrier than the other one. That's actually the best way to distinguish between the two types of images. And it might not learn about, like, hey, what is the image actually showing? So you really need to understand what it's doing and do the data collection in a similar way. We've also found this a lot with the video projects. So we collected a lot of video from webcams, and basically video compression artifacts just completely mess up some of these models. And like, you need to train them to correct for those, because they just mess up the low-level features, the lowest layer of convolutions, and then everything above that is confused. So I think deep learning helps a lot, but I think people still need to think about features, especially when they become opaque like this. Yeah.
That's a really great answer. And also some really great examples to sort of explain that.
Yeah, it's amazing how much of a difference these make. Like you'll, yeah.
Yeah. So somebody here said that they're interested in designing software products for machine learning rather than doing the sort of math and stats behind machine learning. Do you see that as a successful field to get into?
Designing, yeah, that's a good question. So I think, yeah, I think to design useful software for it, you don't necessarily need to like be completely up to date with all the math and theory and so on, but you do need to understand people's workflow. So in some sense, the workflow from machine learning is very similar to any other environment where people run experiments and like summarize the results. It's also similar to a lot of the problems that happen with just data pipelines and data engineering. So how do you reliably run something? How do you fix it when it broke? How do you backtest it? So I think there's a lot of interesting stuff in there that people can work on. And that's actually at Databricks in particular, like we have basically an interactive environment for data engineering and data science and machine learning. And a lot of like the features we're building are to simplify that workflow, to like let people be productive running these experiments on large data sets and like coming back to check the results. And people really appreciate that type of tool.
Cool.
So, yeah.
And since we're talking about Databricks, do you see Databricks as, I always thought of Databricks as sort of the company for Spark. Do you see that sort of shifting?
Yeah, in general, we want to cover the whole kind of analytics and data science workflow. So even with Spark, so we're using, obviously, we can give really good, we can have really good products around Apache Spark because we know a lot about it. But even there, when people use it, they use it in combination with something like scikit-learn or TensorFlow or various Python libraries, OpenCV, stuff like that. And, it's a programming environment where it's really easy to connect those. Like one way to think of Spark is it's kind of a glue to build a distributed workflow and run it reliably. But inside it, you can use many of the standard tools. So people use these, and we've also built and published like pretty interesting integrations with things like XGBoost and TensorFlow to make them very easy to run together with Spark in a large-scale setting. So we're definitely focusing on the whole workflow. Yeah.
Ah, cool. And then final question, where do you spend most of your time? Are you spending it at Databricks? Are you spending it at Stanford, other startups?
Oh, yeah. No, definitely not other startups. One startup is enough. I split my time between Stanford and Databricks. It kind of depends. Like usually throughout the school year, I'll spend more time at Stanford, but then summers, I'll spend full time at Databricks. And also I go up like at least one or 2 days a week to continue doing projects during the school year. So it's I'm doing different things. As I said, like Stanford stuff is more researchy. It's like a few years out, but the Databricks stuff is like, hey, what can we build today that kind of solves people's problem? But it's really interesting to see both, like what do a lot of users need to do like right away, and also where is the field heading, and think about how we can maybe incorporate and plan for some of these ideas in like future software. So yeah.
Cool. Well, thank you so much for joining us. Really honored to have you, and I hope that all of the participants enjoyed this Data Science in 30 Minutes. As I said, we had over 2,000 people sign up for this, and we're very excited that you'll have a sort of audience, and this will live on beyond this live session as a YouTube video, and I'll make sure to send a link to that so you can share it with all of your followers. And for those of you who are attending,
okay, perfect.
Yeah, perfect. For those of you who are attending, if you're interested in our free fellowship for PhDs and master's students to learn more about data science, you can apply online at thedataincubator.com. And we hope you'll join us for the next installment of one of these things, where we will have Ian Swanson, who is the co-founder of datascience.com, speaking with us. And that will be next month. So, all right, thank you so much, Matei, and goodbye to everyone who's watching us.
All right, thanks a lot.
Cheers.